Welcome to the second in the talk series, the Institute Colloquium called Samvaad. This is basically a research talk series. So in Germany there is a saying for academics. It's called Akademische Viertel. That means it's called academic quarter. So as you know, Germans are very strict about time, right? And but they make an exception for academics. They say that if you're an academic, you can go 15 minutes this way or that way. So you have a leeway of 15 minutes. And so it's a very academic colloquium. So we are just getting started as people drop in. So the next talk in the series is by Professor Amit Chattopadhyay, and his talk is on geometry, topology, and computing from the pure maths department from our, right? And Professor Sachitra will be the session chair.
So good afternoon. I'm sure all of you have seen Professor Amit's bio on his website, but there's just one thing that I wanted to add, which is something that he shared with me. So after getting his first master's in mathematics, he apparently got an offer to continue on a PhD in the same program, but he got slightly frustrated with his project, which was on zeros and polynomials, so he wanted to switch to something more practical. So he chose to do something in computer science, but unfortunately he's finding that he still has to find zeros even in computer science. And I'm guessing that's something that he will enlighten us all in his talk today. So please. So again, keeping in the spirit of Samvaad, it has to be a conversational effort, and we'll try to wrap up by in about 90 minutes. That's the plan. Yeah, thanks.
Thank you, Sachit, for your introduction. And you will definitely see a lot of computation of zeros in my talk. So this talk is, so in this Samvaad session, actually, I'm planning to introduce you with three of my research topics, which are you'll see from the top, the certified geometry computation, topological data analysis, and fiber surfaces. These are my current research topics. And this falls under the area of geometry and computation and topology. So geometry and topology are the two very important branches of mathematics where they study about shapes. So geometry studies about the local properties of the shapes. For example, if you want to find the curvature locally on a shape, or if you want to find some area or distance between 2 points on the shape, those are the local properties they study in geometry. Whereas topology studies the global properties of the shapes. For example, how different components of a shape is connected, and number of tunnels, number of holes in the shape, that is studied in the topology. So those are the global properties of the shape from where we can classify different shapes. So the goal of topology is to classify different shapes into different classes. So that's the ultimate problem they try to solve in topology. So in computation, we try to find different properties of geometry and topology for getting better output, for getting, we call it certified output. So you will see the meaning of certified in a couple of minutes. So in certified geometry computation, what we try to do, we do not focus only on the numerical accuracy. We focus on the whether the output is topologically correct or not, whether that is certified or not. So that is the goal we have in certified geometry computation. For example, suppose let's take this example of shape reconstruction, where we try to reconstruct a smooth shape from a point cloud. So there are many different methods for doing shape reconstruction from a point cloud. For here, we try to focus on a particular method called implicit function method. That method works in two steps. First, you reconstruct a function, which is a good function that should have some kind of property. And in the second step, you extract an isosurface from that function which will represent this point cloud as a smooth shape. So 2 steps. First step, you reconstruct the function. In the second step, you extract the isosurface from the function. The second step is called isosurfacing. So the first step requires some kind of guarantee on the point cloud, some kind of sampling criteria, which is depending on the machine by which we capture the point cloud. So there we cannot have much input unless and until we see the output. So we will not focus currently on that topic of giving a sampling criteria which will give you a good function. What we'll try to focus on extracting an isosurface from that function. So basically you need to solve this kind of equation, right? You need to solve this equation of fxyz equal to 0. So there we need to find some zeros of a function, okay? And the goal we have for solving such kind of equation is the output should be topologically correct or kind of certified. We'll define topologically correct. So that should be kind of equivalent to the given point cloud or the original input what we want to compute. So do you know any method for extracting an isosurface from a smooth function or a scalar field? Any method? Jayad should be right. It's a matching cube. So that's the most popular or most famous algorithm which came in 1987 in a SIGGRAPH paper, its most cited paper in computer graphics. And what we do in matching cube, we given a function, say we are considering here matching square, not the matching cube, because it's difficult to visualize in there or in matching cube. So what we do, so suppose we are given a function in this plane, in the planar domain, and so that what does it mean? So we are giving the function values at each point of the grid. And so from there, we compute the sign of the function at the grid points. So we'll have some kind of sign pattern for each of these boxes of the grid, right? And we have a lookup table which is given by matching square. We match that lookup table with this sign pattern here in the grid, and we try to approximate the surface or the iso line here using this lookup table, okay? But you can see that so this curve here is actually the original curve which we want to reconstruct or want to approximate, and these lines are actually giving you the approximated iso line what we want to get, right? So you can see that the first and the fourth figure actually giving you the correct result. So the original shape and the approximated shape are kind of equivalent. So you have one component here, and the approximated shape is also one component. You have two components here, the approximated shape is also having two components. Whereas in the second and the third figure, you can see that there is this number of components in the approximated shape is different than the number of components in the original shape. So basically matching cube fails. So why is that? Why is it failing to approximate? Can anybody guess? Anybody can guess that why it's not able to compute the correct shape? It's written here actually. So the matching cube doesn't provide any kind of criteria on the grid size. So you just take an arbitrary grid and compute the sign pattern depending on your function value, and then you use the lookup table for computation, for computing the approximation. So instead of this grid, if you take even a finer grid, more refined grid, then you will get probably the correct output. But there is no guarantee when you will be getting correct output. So it doesn't provide any criteria when to stop your subdivision algorithm. If you are applying some subdivision, when to stop. So that is the issue we'll address in our algorithm called certified algorithm. So this kind of problem we solve in certified algorithm. Okay, where we'll be giving some kind of criteria on the box size, and it will terminate, the algorithm will terminate automatically and will give a correct result all the time with some theoretical guarantee. So before going into the algorithm, so let us give you a brief idea what do we mean by certified, right? So we are all the time saying that certified, what do we mean by certified? The certified means topologically correct. Topologically correct is measured by different properties in topology. So those are called homeomorphism, isomorphism, or isotropic. Okay, so there are definitions in topology, but what I will try to tell you that when two shapes are isotropic, one can be continuously deformed to the other without, there are certain property also must hold, without any self-intersection or something. For example, this your coffee mug is isotropic to donut. So you can continuously deform your coffee mug to a donut, or the other way around. You can continuously deform the donut to a coffee mug. Okay, so these are topological equivalent. So in our computation, if we want to compute the donut and if we are getting a coffee mug, we are still okay, we are certified. So although they look different, but yes. Which one?
All continuous shapes.
Yeah.
Isotropic to each other?
No.
No.
No. So you cannot continuously deform in that previous picture what I had shown to you. You cannot continuously deform these two components, which is given by these bold lines, to this shape. Certain properties also needs to be held. They shouldn't self-intersect. So if you want to try to do that, there will be some self-intersection in between. Then this property will be lost. Okay? So isotropic is a very strong property in topology. Homeomorphism is little bit weaker. So when some shapes are homeomorphic, they are isotropic. When two properties are isotropic, they are homeomorphic, not the other way around. For example, if you consider these two shapes, one is a torus and another is a sphere, they are not isotropic. So not isotropic can be proved by computing some kind of topological invariance, because if two shapes are topologically equivalent, then certain properties remain preserved. Okay, so those are called topological invariance. For example, if you cut this torus along this red circle, it will disconnect the torus, but number of components will remain the same. So it's still one component, right? But you take the image of this, and there will be always a circle like this. The image of this will be a circle on this sphere. And now if you cut this sphere along this red line, it will disconnect the sphere. So there will be two components. But here it's not disconnecting. So the connectivity component, the connectedness is one topological invariant. So if we say that this connectedness property is not preserved by cutting along these lines, red lines, then we say that these two are not isotropic. Okay. So in our computation, if we want to compute a torus and if we are getting a sphere, that is not topologically equivalent. Similarly, for these two are not isotropic, you can see that if we cut this along some circle on this kind of pipeline like this, then it will disconnect, but it will not make any new component. But whereas if we take a circle over there, and if you cut this will make two components, so it will be they will not be isotropic. Okay. So this kind of computation are not allowed in our method. So if you want to compute this, if you are getting that, that is not certified. So isotropy, as I have already explained, that these are one can be continuously deformed to the other without any self-intersection. Yes. Okay, so we need a computational model for our algorithm. So far I have explained the mathematics, but if we want to do such kind of computation, we need to make a different computation model than the merging cube. Okay, so what model we use? So in our model, we use a method called interval arithmetic. So like you do the real arithmetic, so addition, subtraction, multiplication, division of two real numbers. Similarly, there are libraries for doing the similar computation for intervals. So if you take two intervals, you can add them, you can multiply them, you can divide them, or you can subtract them. So basically the interval arithmetic, so given any kind of scalar field, you can define the corresponding interval version of the function. So which takes one interval from the domain and its output will be one interval in the range. Okay, so that is what it is defined here. So you take one interval from the domain and you take the mapping or the image of that with the function and get one interval in the range. Okay, and this range you may not be able to, the libraries are not giving us the exact range, but so they are conservative. That means that the actual range will be the subset of the range provided by the library. And another small property we use, so we subdivide the domain into small grids. For the exact computation, we consider the vertices of the grid as the dyadic numbers. So if you have heard about the dyadic numbers, they have finite binary expansion. So this will be of the form m to the power minus n, where m is an integer and n is a natural number. So all the vertices, so what is the assumption we are making? So these numbers are dyadic numbers, and our function could be computed, the sign of the function could be computed exactly at those dyadic numbers. So our function we may not be able to compute the sign of the function at a floating point if we subdivide arbitrarily. But we subdivide the domain in such a way that at those dyadic numbers, we are able to compute the sign of the function. This is the assumption we make in our computation for the exact computation. So, okay, so interval arithmetic I have already explained. So these are whatever I have explained. So you take two intervals and compute the corresponding addition, subtraction, multiplication. So there is a library called Boost Interval Arithmetic Library. That is what we use for our computation. Okay. So let's now come to the computation. So I will show you just for a function of single variable. Okay. So the goal was to solve the scalar field like f x y z equal to 0. So instead of that, I am just showing you fx equal to 0. So you have a signal like this, or a function like this, and we want to find the 0 of the function. So what is the meaning of certified computation in terms of function of single variable? We want to find the isolated intervals. Each one will be containing exactly 1 0 of the function. Okay, so what we do, we set two predicates based on the interval arithmetic. First one, so these box functions are the interval functions. First one says that f has no 0 over this interval I, right? And the second one says that f dash I, this interval corresponding to this, doesn't contain 0. That means that f is monotonic over this interval I. So these two predicates we set for our computation. Now what we do, we subdivide the interval corresponding to this function. So this pink line, we do not subdivide anymore, because so we subdivide until this C0i or C1i are satisfied. So in this interval, C0i is satisfied because it doesn't contain any 0. So we stop subdividing that part. But the other part, we haven't yet decided. We subdivide that further. This part we can again ignore because this doesn't contain any 0. But this part, the first condition is satisfied, but the first condition is not satisfied, right? So we'll subdivide this further. This one. So the thing is that that is also an order. So first we look the C0i. Okay. If it is not satisfied, then only it will go to C1i. Okay. So next. So here we terminate. This one is also discarded. This one is giving you the 0, and also it's giving you some guarantee that it will contain exactly 1 0. So that is what we require for the certified computation. And this will terminate when this is non-degenerate, right? This will terminate when it is non-degenerate, means this will terminate when your function is not touching, right? So if it is touching, what will happen? I will not tell you. You think. So if it is intersecting this line, then it will terminate. This algorithm will always terminate, and if you have thousands of roots, it will give you thousands of intervals. Each will contain exactly one root. The multiple root means, okay, in this interval whether there are multiple roots, that will always be detected by this second criteria. So it will subdivide that many times, that many roots you have in that interval, and it will always extract exactly one interval corresponding to one root. So one interval will not contain more than one root, yes. So not C0, then it will, not C0 means it contains a root, and intersection C1 means it is monotonic. C0, yeah, so that means it doesn't contain the root, yes. Okay. Yes.
How do you know the interval? Like you said about the thousand roots. So how do you know which range you have to take for dividing it?
So range will be given to you. A range or domain will be given to you. Domain of the function. That's what you are saying, right? Domain of the function will be provided along with the signal or along with the function or scalar field, whatever you have. Okay. So I'll not go into higher dimensions. What we do, instead of that condition of monotonicity, that second condition what we have defined there, that is the most powerful predicate what we use. That is bit computationally expensive compared to merging cube, because merging cube is not using that predicate, right? But it will always give you guarantee that you will get exactly that many intervals corresponding to the number of roots you have. So we actually generalize that predicate for higher dimensional domain. For a 2-dimensional scalar field or a 3-dimensional scalar field, we can generalize that, and that is called the small normal variation condition. So over that domain, if you consider the normal to the surface or the normal to the graph of the function, then the angle between the normals will be always less than 90 degree. So that is what is given by this predicate. This is called the small normal variation condition. Also, it's called the regularity condition. So it ensures that the function has no zero, no critical point. The derivative of the function doesn't vanish in that interval. Okay. So using that condition, if we now subdivide, like we have done for the previous case, if we subdivide, then we can see that for this region where the curvature is more for the function, it will automatically subdivide more, whereas here it will subdivide less, and the algorithm will automatically terminate. And when it will terminate, we can prove that the approximated curve is isotropic to the original curve, what we want to approximate. So there we can prove the isotropic. So these two are isotropic. So we get a certified mesh corresponding to an isosurface of a scalar field. Yes? Well, tell. Discontinuous, no, you mean the points? Or small, that will automatically be taken care. Right. We are subdividing the whole domain. Yes, and we are keeping the nodes in a quad tree. So first subdivision, then again next subdivision.
So you don't do any adaptive subdividing?
No.
So you just find the grid size for which this.
I will not find anything. It will automatically terminate when it will be locally isotropic. When these two conditions will be satisfied, we can prove that locally we can always approximate by small either line or a triangle which will be isotropic to the original f inverse 0. So this terminates automatically. We will not interfere the subdivision by considering the grid size or anything.
So any processing you have to do with the grid, you will have uniform grid size?
Yes. No. So yes, that's why our grid size will vary. Our grid size is varying. You see that here there are more. Can you see that? No. Right? Grid size will vary where it is more curvy region. So it will be subdividing more.
That will introduce hanging nodes. Your grid size is going to introduce hanging nodes.
Hanging nodes.
You have so you have squares of two different resolutions side by side. So there continuity.
No. So okay. So you also take care of we also balance the neighboring nodes by subdividing one node further or something. We do some kind of balancing of the tree. So it will be a quad tree for a 2-dimensional function, and is a octree there will be an octree for this 3-dimensional, and we also do the balancing of the nodes so that this problem is not occurring. Okay. Yeah, so maybe we'll talk offline. So this is one problem where we get certified output, right? So I keep this problem for you. to find that you have to find a suitable condition. Yes.
Certified is modulus on minimum grid size.
Certified?
It is certified.
Yes.
Subject to some minimum grid size or something. There's some other criteria you have. Because theoretically you might have to subdivide forever to get
No. Certified for the mesh, whatever you obtain from the algorithm. That depends on your input. That depends on your input. This will always vary depending on the complexity of your scalar field. Yes, so this problem, if you see that we are trying to find conditions for certified computation of singular isosurfaces. Singular means when there will be some point in the domain where gradient of the function will be 0. So there it will go forever if you apply the same condition there. The second condition what we have told in the previous slide, so this will never be satisfied for these singular functions. Okay? So you need some different technique to solve this, to compute these singular isosurfaces. I just leave it for you to think. Okay. So there it will be forever. Yes. For this one-dimensional case, it is touching the domain. Yes, this function is touching the domain. So that means that there will be one point where derivative of the function is 0. Right? It's tangential.
So would it help some kind of a translation function of this?
Translation.
To kind of take the point cloud and
shift it. So translation means you.
Translation, what I mean is to prevent things like where the singular.
There are techniques like perturbation strategy. Perturbation. So they call it perturbation. So there are currently they are dealing this kind of situation by that. Yeah, you are right. Huh?
You don't have an equation for it.
Equation. You don't have an equation. So not.
Yes, singular surface is simplest example is a parabola. Parabola is tangential to say your exact. That's what you mean by singular surface.
Yes, you can also consider that. Yes, yes.
But since you don't have the equation for the parabola, that's why you have all these.
Equation of the surface. No, then also you will have such issue. I mean, without having, if you don't have an equation, then also you can have this problem, right? So you can always have some singularity.
Finding zeros is now solving.
No, we will not consider solving zeros like analytically. So you are talking about the analytical solution of that. We'll do the computation in the machine. Okay. Okay. So this was one problem. So let's talk about another problem. But so this is called a Morse-Mel complex. So you can understand the structure of this complex by considering the flow of rainwater in a terrain. So suppose you have only 3 types of critical points. 3 types of critical points of a gradient system. So there are. So these are the peaks, the maxima. These are the minima. So in the terrain, so where the flow is going, and the downwards, and these are the saddles, that in between 2 peaks. Okay. So you can think when the rainwater is falling from the peaks, so it will form some kind of quadrangular region where the flow is confined only in this quadrangular region. It will not go from here to here. Okay, in the ideal situation I am talking about. In the real terrain there are a lot of complications, right? This is the ideal situation. So it will form some kind of quadrangular region. Your gradient, the direction will be coming from the peak to the minima, and it will not cross these boundaries. These boundaries are called the separatrices. So they separates the flow. Okay, they separates the flow, and it will form this kind of quadrangular regions. And this kind of structure is applied in understanding the data, the scalar data or the vector field data. In topological data analysis, you will see that this kind of structure is used to understand different properties of the data, and also for matching. Like if you have two different shapes, if you compute two different Morse-Mel complex corresponding to that, then you match these complexes to see whether the shapes are matching or not. So by that way we can have some kind of application of. So our problem is to compute such complex corresponding to a gradient field. Corresponding to gradient field, we want to compute such complex. But there are a lot of issues if you want to compute such kind of complex. So first of all, we have to find these critical points, right? Critical points and their boundaries. Critical points and their boundaries. But critical points are just the points. It's a zero-dimensional entity. It's a zero-dimensional entity. So you will never be able to find the exact location of the critical point. Okay? And so suppose instead of this critical point, you are approximating it somewhere else nearby, and you start from here to find the gradient direction, and every time all the numerical methods whatever we have available, so they will always, they are error prone. So there will be always some error incorporated when you are computing, and you will go somewhere else. You will never become to that critical point where you want to go. So you'll never be able to. So by using these numerical techniques, you will never be able to compute such Morse-Mel complex. Yes.
So this is exactly what all the deep learning guys do, right?
Yeah.
You would have seen they're also trying to find these using these gradients, those optimal weights and so on, right? For all of those
yes.
training the networks.
Yes.
And they are now coming up with various kinds of techniques to help get past all these problems of saddles and
yes.
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 So are there any kind of techniques that maybe what you have developed which could be used by them or vice versa?
I don't know. We have developed one technique, but I don't know whether they can use that technique. Okay, I'll just show you the idea. I'll show you the strategy how we are solving using this certified computation paradigm. Okay. So this is the thing I was trying to tell you. So if you start from a point, you will never reach the exact critical point where you want to reach, but you will reach somewhere else. Okay. So we'll not be able to use numerical computation, because that will always give you wrong result, and you will not get the correct, the combinatorially correct Morse-Mel complex. So I'll just tell you the idea of what we are doing. So suppose we are just taking one quadrangular region, one quadrangle. So what we do, we subdivide the domain like we have shown you in the previous problem. We compute the isolated intervals corresponding to each critical point. So we are giving a guarantee also that each box will contain exactly one critical point, one saddle, one minima, one maxima. And these boxes will satisfy some more properties. The boundary of the boxes will satisfy some more properties. And what else we do? For the separatrices, we compute a funnel-like region. That is also certified that one funnel will not contain more than one separatrices. So these funnels, if there will be kind of a disjoint funnels, they will contain exactly one separatrix. And also prove the convergence of this algorithm using the technique. Yes.
There's not corresponding to any box. In some parts the box is very good, some
curve.
The funnel that shows, is there a grid box
yes.
for each part?
Yes. yes, yes, yes.
And then it will also, but it will be, there are different sizes.
They can be of different sizes, but they will not, two funnels will not overlap. Or kind of, they will not have, they are always isolated.
And another question is so for terms of dimension, that is, how feasible it is
when we are increasing the dimension. So this is done only for 2 dimension until now. And yes, so this is also, I mean, we face a lot of challenges in computing this in 2 dimension. Yes, 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 yes. So we have extended that over an implicit surface. So that is also 2-dimensional. You can say it's also 2-dimensional manifold. It's only a surface. So from plane to the 2-dimensional surface. That's what we can do until now. And for 3 dimension, I have the open problem for you. For 3 dimension, we are still struggling because there the separatrices are not only one manifold, but also a surface, 2-dimensional surfaces.
There's a problem, like there's no algorithm or it's not efficient.
There is no algorithm. There is no algorithm for computing. I mean, you can approximate like numerical techniques, but there is no algorithm for computing. So there is no guarantee that you will always get a correct output. Yes. No. Computational error means. We have computed. Okay, okay. I haven't shown you any output, but you can see that paper.
Okay, so how you avoid the computing errors so even when you do that.
So we are using the same techniques like interval arithmetic and some properties we need to satisfy for this when you are subdividing the domain for the funnels. Okay, it's combinatorial technique. It will always converge to the so one funnel will always combinatorially converge to the other critical box.
So isn't it like you have funnel and then you calculate it and then you get the result?
If you have funnel, you can do a lot of things, but computing funnel is difficult. Okay. Yeah. Okay, so another problem I think we can just maybe the second topic also, and then we'll stop. So another problem is it's called Jacobi Set. This is also another, so we know that critical point of a function, critical point of a scalar field. So if you have 2 scalar fields which are interacting with each other, so then the critical points are equivalent to the Jacobi set. So if you have bivariate field or a multivariate field, so you have many scalar field like you can just take an example like pressure, density, this kind of fields, right? So if you have multiple fields, then so these red lines, so you can see that for the first scalar field we have some kind of contours, second scalar field we have some contours, and in this at these red points the contours are touching from one scalar field to the other scalar field, the contours are touching. So these are called Jacobi set, and these are very important because these are the points where topology of a bivariate field or a multivariate field changes. Okay, and at those points we have this equation satisfied. The gradient for the first scalar field, cross product of gradient of the second scalar field will be 0. So for the first one scalar field, you have only gradient of f is equal to 0, right? For 2 scalar field like this. For 3 scalar field, you can extend this definition in a different way, but there are still, I mean, there are still definition where you can compute the Jacobi set corresponding to multiple scalar fields. Cross product of?
Cross product is typically useful for 3D structures. In 3D you can consider cross product to get something that is tangential for both those planes. Let's say that we're taking an interdimensional matrix. What is the equivalent of the cross product?
Now, equivalent of cross product or manifold, or you are talking about the gradient, n-dimensional.
The cross product I can understand for the
Cross product of two vectors. Yes.
So what is the equivalent when you are talking about n-dimensional? Like let's say
So the cross product actually is defined until the 3 dimension. Okay. After that you have some other definition, but there will not be kind of geometrical meaning what we are getting here, right? So yes, yes. So there will be different definitions where you can extend those, but not. I mean, if you see the geometry, you want to see the geometry, then it's until the 3 dimension. Okay, but here the Jacobi set definition we define, like if you have n fields, like you consider the, like in this definition we are considering the projection of the second field on the contour of the first field, and then you compute the critical point of the projected field. That will give you the Jacobi set. If you have n fields, you consider the one field which is projected on the intersection of n-1 contours of the n-1 fields, and then you compute the critical point of the projected field on that intersected manifold. So we compute in a different way, not using the cross product anymore. So this is true only for 2 and 3 dimensions. Okay, but computing this Jacobi set is important and it's challenging also. So if you consider these 2 fields instead of those 2 fields, so this is the circle field and this is called egg field. So it's another field, and if you want to compute the corresponding Jacobi set, so I tried with Mathematica. So this is the most powerful tool I have in my hand. So I was trying. So you can see that in the center, we are not getting a correct output. It breaks. So Mathematica breaks for computing such. Okay. So one of my students was working on this problem, external project student. So we have come up with one solution by using the technique of certified computation. So we are able to, although there are a lot of subdivision inside, but these are the degenerate point, and it's difficult to handle, and Mathematica cannot handle that. Okay, so so we subdivide and get that output. Okay. Okay, so let me stop here for this problem. In conclusion, what we can say that we have seen that certified geometric computation is essential for getting correct output, right? So we have seen that certified computation in isosurfacing, in computing Morse-Mel complex, and in computing certified Jacobi set. So there are many open problems and challenges in this domain. First one is singular. So there are certain techniques by which you can compute the singular isosurfaces, like you have told about the perturbation technique, but still the problem is not solved completely. So perturbation needs also some kind of guarantee and the detection, right, when you need to give the perturbation. And for the Morse-Mel complex in 3D, it's still open. I'll talk about the fiber surface. There is another kind of surface where it is also required, because there are a lot of discrepancy in the output. We are not able to compute the correct output for given scalar fields. Okay, so any questions? Yes.
Basically implies topological equivalent, but is that sufficient? Because the conflict of
What else you want?
For a coffee cup, clearly is not a donut, right? I mean, there has to be some notion of how
accuracy. Accuracy. So once you can compute the certified output, you can subdivide the domain further to get more accurate curves. So that is easy part. That is the easy part. So that is.
And several options, like the coffee cup and donut, can more things also be the same? So
Yes. Yeah.
then when we classify, you would still have that.
Yeah. So they are topological equivalent. But when in the real computation, if you want more accurate, like if you want the coffee mug to be more close to the donut, so I mean in this case you are getting the from this shapes from the same function, right? So there it was little bit different, the example what I had shown you. But when you subdivide the domain further for all the examples what I have shown to you, like for this example, so here we are getting a straight line kind of thing, but here we are getting a curved line, right? So if you subdivide this domain little bit further, you will get the close to this, but that will be a little bit more computationally expensive. Our next topic is topological data analysis. So here the goal is to extract feature from the data, certain kind of topological features. So the data, what we mean by data here, so we have a scalar field, like this is the electron density of a hydrogen atom, and this is a simulated vector field. Okay, this is a multi-field where multiple scalar fields are interacting with each other. Like this is the data taken from the cosmology data, where we have the white and dark matter. Okay, that's a simulated field, but more than two scalar fields are there. And this is, there's a point cloud. So what kind of analysis you want to do using the topological data analysis? We want to compute the connectivity of different components. The component also has certain meaning, like the contour is a component, contour of a scalar field. And we want to compute the higher dimensional holes like tunnels and voids in the shape. So these are also used in molecular biology, where you want to see some kind of tunnels in the data. Computing position of the where topological changes are happening, some kind of change where one component splits into two, or some other kind of topological properties are changing. Or do you want to simplify the data using the topological simplification to understand the data in a better way? Okay. So I'll show you one example. Okay, first of all, there are tools in computational topology where so the simplicial complex is for approximating the domain of the data. So we approximate the data using some kind of simplicial complex, or in terms of planar domain, you can say triangulation or tetrahedrization. Those are called simplicial complex. Simplicial homology studies the holes in the data. So holes or tunnels in the data. There are topics like persistent homology, which studies of the birth and death of components. Like if you consider this is a one-dimensional signal, and if you just scan the data from the bottom to the top, using as the function value grows, so you'll see that different components, so these are called components. The bottom part of these blue lines, they are merging or splitting. So this kind of change of properties are called the deaths and births of the components. So this is just for one dimension, but you can also do this similar thing for n dimension. If you have an n-dimensional data, and if you have some kind of direction along which the data is increased, the value of the data is increasing, so you can do the similar techniques, and you can study the changes of components, like some holes are created, some holes are disappeared, this kind of changes we study in persistent homology. And so the Morse theory, we'll see again, the Morse theory is a very efficient tool in topology, what studies about the critical features or the critical points. So if you consider a scalar field, and if you find the critical points of the scalar fields, those are the points are most interesting in topological point of view, because those are the points where some topological changes happen. So I'll come to that slide, that picture again. But before that, so using that Morse theory tool, we can skeletonize the data. So these are kind of skeleton of a scalar field, which is called a contour tree. So like you do in your ML or neural network, you subdivide the data or you classify the data or cluster the data into different groups. Like, so what we also do in topology, we split the data into different components, and so those are the region which will be of equivalent region. So all the components, all the contours are there will be of equivalent in nature. So we can also subdivide the data and try to make a skeleton corresponding to the data and understand the data in a better way. Okay. So without using the machine learning techniques, of course. So this is also another kind of data structure called Reeve graph, corresponding to a field, the height field on this shape. So this is the data corresponding to that. Morse-Mel complex we have already seen before, corresponding to a gradient vector field. You can compute the Morse-Mel complex. So let's talk a little bit on this topic of multi-field simplification. So what we have seen here in this picture, this is a scalar field, and corresponding to that we can have a skeleton called a contour tree. Okay, so this is the simplification corresponding to this data. If you see this data structure, you can understand what is there in the scalar field immediately. Corresponding to a vector field, similarly we have this Morse-Mel complex. But what was missing is the data structure corresponding to a multi-field. Multi-field means this kind of data structure, data. So where there are more than one scalar field. So the goal is to subdivide the data domain into some kind of simple regions based on the critical point analysis. So the critical point corresponding to a multi-field, we have already seen, is called the Jacobi set, what we are trying to compute in certified computation. And so the goal is to find some similar kind of data structure which will subdivide the domain into simple regions and compute a skeleton corresponding to a bivariate or a multi-field, which will help us to understand the data. So for that, we need to understand a little bit of how this scalar field is skeletonized. Scalar field is skeletonized by the Morse theory. Morse theory, you can think about when you dip a donut in a coffee mug. So suppose the first part is now dipped, and you are getting a contour, these red lines, right? Red contour there. Now if you dip it further, you are getting a contour like this. So there is a change now. So if you dip your donut in the coffee mug, first you will be getting a contour like this, and then this is like H-shaped contour, and then you will get two contours. The interface of the coffee surface will be making two contours with your donut. Okay, so you can see from 1 to 3 there is a topological change, from one component to two component, and this is the point where this change is happening. So this is the critical point. So this point is the critical point where your topology of the contour is changing from 1 to 2. Number of components is changing, right? So this is also captured when we are dipping the donut in the coffee. We are also forming a graph like this. It's called the Reeb graph. So from 1, then 2, then we have 2 components in 3. So this is captured in this graph. You dip it further, and you are getting an H shape like this, which is equivalent to the critical point. Right? 2 components are merging. There is another topological change, and then you dip it further, where you are getting only 1 component here, corresponding to 5 here, and then it is vanishing. After the 0.6, it will vanish. Okay. So the Morse theory says that critical point of the contours corresponding to the scalar field will change only at the critical points. Okay. And the Reeb proposed this graph almost 10 years after the Morse theory for capturing the topological change in a graph. Okay. So this is actually the partitioning your scalar field into different components. Okay. So this is just clear. So how this Morse theory is working for this. So given a scalar field, we can always compute a Reeb graph, and that will partition your scalar field into different components. Corresponding to each edge here, you will be getting a component in the scalar field. Okay, any question? So we want to generalize this structure for the bivariate field. What will happen when 2 fields are there instead of 1 field? What will happen? I mean, theoretically there are some data structure already known. It's called the Reeb space. So there is a generalization of Reeb graph for bivariate field. But although those algorithms, there are no kind of good algorithms for computing the Reeb space. So what we do for 2 fields instead of this. Okay, first let me show you that this is the contour tree. So that is equivalent to the Reeb graph when your domain of the scalar field is a simple domain. So there it was like a donut or the torus. So that's not the simple domain. You cannot squeeze that into a point. But here this is a simple domain because you can squeeze this to a point. So here you will not have any kind of loops in the skeleton. Here you will not have any kind of loops. That's why this is a tree. That was a graph. That was a Reeb graph. It is a contour tree. So it will not have any kind of loop. So the idea is the same, that we can compute the contour tree corresponding to a scalar field. And the topological changes are happening only at the critical points. So you can partition this data into by computing some data structure like this. It's called contour tree. Okay, so you want to generalize this skeleton. So that is the idea for 2 fields. I'll not show into details, but just to give you some overview how it is done. So instead of contour for a scalar field, we consider fiber, which is the intersection of 2 contours corresponding to 2 different fields. So suppose we have 2 different fields, 2 different scalar fields, and these are the isosurfaces of the scalar field. This is also another scalar field, which these are the contours or the isosurface corresponding to the second scalar field. And what we consider? We consider the intersection of these contours here and that contours, all the contours from the first scalar field, and take the intersection of them. So these are the intersection. So these are called the fibers. Instead of contour, we call them fiber, and the fiber component. So each connected component of the fiber is called a fiber component. Okay. And now, there, as we have done for the classification of the contours using the Morse theory, here also we do the similar kind of classification, but computing the generalized critical points, which are called the Jacobi set. And then we detect the corresponding, so these are the Jacobi set corresponding to, so when you consider two fields, so these are the Jacobi set, and we partition the data based on the contours which are passing through the Jacobi set. So this is a little bit difficult to understand, I know that. So basically the contours or the fibers which are passing through these red lines, these are called singular fibers. Okay, these are called singular fibers, and those singular fibers will partition your domain into small classes. Okay, and then you will get a structure like this. So this will not be a graph anymore. So you'll have sheets instead of the edges of the graph there. Here you will have sheets. These are called the so the sheets of the Reed space. Okay, and we can subdivide this further. So we can subdivide this further into a skeleton by here it is easy to see, but this might not be so easy in some complicated data. We can find some kind of skeleton like this, which will, so here these are the equivalent of these critical components, and these are the regular components, so this will be a graph-like structure, which will be more useful than the Reed space to extract, to understand the data when we have bivariate data. Okay, for more information, you see the paper. Okay. Okay, this is how we compute that data structure. That is the mathematical part, what we have shown. But I will not go into the details of how we compute this little bit. So basically, we subdivide the domain for the first field into some kind of slabs, and then we also do the similar thing. We consider the corresponding the contour tree. But what we do for computing the Reed space, we take the intersection of these slabs and compute the graph corresponding to that. Okay, and then we get a structure called joint contour net, which is an approximation of the Reed space. Okay. So this, for a simple field, we have computed the Reed space in a structure like that, and then we subdivide that further to compute a graph, which will be related to the data in the domain. Okay. Okay, here also there is an open problem. So design an algorithm for computing Reed skeleton directly. So what we have done, we have computed first the Reed space and then the Reed skeleton. But what is done in the contour tree algorithm, they see the evolution of the contours corresponding to the scalar field. Evolution of the contours for the scalar field, and then they try to compute the contour tree. So ours is two-step method. First compute the Reed space and then compute the Reed skeleton. So what we want to do, we want to do a direct algorithm for looking at by looking at the evolution of not the fibers anymore, but fiber surfaces, for capturing the topology of the fiber surfaces using a skeleton like Reed skeleton. There are few applications we have done. This is the nuclear fission data, where we have proton and neutron densities of a plutonium atom. Okay, so this is a bivariate field, and what we do, we compute so you'll see that this is the approximation of the Reed space, but this is a graph-like structure. It's difficult to compute the sheets, right? So we compute a graph-like structure, and then we simplify the data using the for computing the rib skeleton. Certain algorithms are involved there, and at this point, so this is a critical node. We show that this split is happening in the geometry. So this is the point where nucleus splits. So basically what we do, we have a time varying data. So at each time step, we compute the JCN, we compute the rib skeleton, and whenever we see this kind of fork-like structure, we try to see the geometry, by which we can detect that where exactly the nuclear scission is happening. So recently we are trying to work on the same problem in a different way. So what we do, we find the distance measure between, so we have a time varying data corresponding to each time step. We have a bivariate field, okay, and we construct the rib space corresponding to each time step, find the distance between the rib spaces, and plot. So the distance is measured between the rib spaces, and plot the distance between two consecutive time steps. And you see that at this time step 690, there is a big jump. Okay, so this point, this time step will be giving you the point where there is a nuclear split. Okay, so we extract the. So this is done by one student at IIIT-Bangalore. So was working in the CSA department. So this is his master thesis. Okay, so these are the applications, and we'll stop here. So we have seen that topological data analysis helps to understand the features in the scientific data. Okay. So multivariate topology, not much work is done. It started very recently, and there are a lot of open problems in this domain. And so the few of the open problems like a direct rib skeleton algorithm, what I have already told you. The first is rib space algorithm. There is one algorithm, although nobody has implemented, only one algorithm what we have implemented here, that is very, very slow, the JCN algorithm. So we are looking for a faster rib space algorithm for capturing the bivariate topology. And also there are challenges like data structure for capturing higher dimensional features in the scientific data. Okay. So I'll conclude here today. Thank you very much for your attention.